Hello, Philippe. Thank you. Hello, everybody. Welcome, and thanks for attending. This been a long journey for everybody, I guess. I'm going to start sharing my screen. Right. I hope you can see my slides. Philippe, can you confirm my slides are visible?
I can't see them yet.
Yeah.
No?
Yes. Yeah.
Yep. All right. Okay. So here we are. Memory utilization, leaks and stalls. Okay. First, just a very quick bit about hardware and the OS. This talk is designed to go over like 1 hour and a half, perhaps 2 hours. So I'm gonna very quickly skim over some slides. But let me introduce you. Before long ago, the CPU and the RAM had very similar speeds, but as time has advanced and the CPUs have improved their performance, RAM speed has started to fall behind. And so that's why it concerns us so much. This is a story about nanoseconds. Like all the memory performance is about nanoseconds. So we're gonna be referring to many figures which are measured in nanoseconds. Again, this is, I guess I have fun with it. You should take a look at this video from Grace Hopper, where she explains that we are bound by the speed of light in computers, and that the maximum distance light can travel is in a nanosecond is 30 centimeters. And so computers are limited by that. And that's why we have to mind our nanoseconds, because every operation we do takes time. And so we have to be cautious and save our operations and our nanoseconds. Okay, so this is how CPU versus RAM speed has evolved. You can see the gap has really widened. And this is basic memory hierarchy, where you can see at the bottom the cheapest and the largest capacity memory, which is mechanical hard drives. Then we have solid state hard drives, which are smaller in size, but and not so cheap, but they are much faster. And then we have RAM, which is again it's scarcer but faster and more expensive. And then we have the ultra expensive level 1, level 2, level 3 cache in the CPU itself. And then we have the processor registers. So this is how we have coped with that memory's performance gap. By adding this cache here, we have helped the CPU to keep up. But so this is the basic idea you have to have when using memory. You really want to stay here or here and try to avoid going here as much as you can. Okay, so level 1, level 2, level 3 cache, these are built into the CPU, super fast. They have rather small sizes, and increasing their size indefinitely will not help, because the latency will increase, and so they will not be so efficient. These are reference figures for a Xeon latest generation. And this is the performance you could expect from this cache. So 4 cycles in a modern CPU are about 1 nanosecond. So a level 1 cache hit is 1 nanosecond, more give or take, choose. And so this takes us to something, which is the importance of level 1 and level 2 hit ratios. So when we have 100 requests, if all of them hit the level 1 cache, we will spend 100 nanoseconds. But if only one of them misses the level 1 cache, then it won't be 101 nanoseconds, but it will be 105. And if actually the data is not sitting in the level 2 cache, but rather on the level 3, then it will be 155 nanoseconds. And if actually the data is sitting on the main memory, then it will be 255 nanoseconds. So the simple 2-3% level 1 cache miss turned out to be 150% slower. So that is why we care so much about level 1 and level 2 cache hit ratios. And that's where we're going to see some tools that allow us to observe the hit radius of the level of the cache. So on the full length talk, I will extend on the virtual memory manager. And I will explain how it simplified memory management long ago, back in the 80s, how having a virtual memory manager was a great thing that helped programmers simplify their code and helped them achieve stabler code. It allows overcommit through swap. It isolates threads in memory so they have safe security, so they are secure and they can read each other's memory. It handles, again, the paging and the swapping. And we have a multitude of tools that allow us to introspect it. Oops, sorry for that. So next on the OS is the memory allocators. These handle the virtual memory allocation to the, and they provide user-land routines for the memory management. There are many choices. Each has its own trade-offs. Our favorite is usually jmalloc, Google's own tcmalloc, and then we have also glibc from the Linux distro. Very easy to change by setting LD preload, environmental variable. And there are multiple tools, but each depends on the allocator. Jmalloc has a built-in profiler. tcmalloc also has a gperf tools profiler. And we have glibc util sleep mem usage. And so there's ways to actually look at this, but it's not the main focus of our talk. We also have THP, transforming huge pages, usually debated. In the computer, there's something called the translation look-aside buffer, which translates virtual addresses to physical addresses. And basically, this TLB has a limited size. And the larger our data bank have grown, the more impossible it has been to fit all the physical addresses in the TLB. So what happens is that there are many times misses in the TLB hit ratio. And so what the transparent huge pages try to do is map more memory into a smaller number of pages so they will fit the translation look-aside buffer. But it has proven to not be very useful for many database workloads because it becomes fragmented, and then scanning over the virtual memory happens, and also the fragmented pages have to be collapsed, and also jmalloc, because of the way it works, it ends up leaking. So these are known problems with THP. You can observe them with sar-h, and with you can observe the TLB hit ratios with perfstat. We're going to take a look at that later. So then NUMA, also it's something that came as we added more CPUs to our computers. The classic unified memory access pattern had a logarithmic performance degradation. So the more concurrency you had, the more performance degraded. And NUMA, what it did is it split the memory access into multiple banks. Each CPU will have its own memory bank. And so the local access will be very cheap, while the remote access will remain at the same cost than before with log n. But because now half of the access is super cheap, we gained a lot of performance. And actually, if we can keep all of our access local, then performance is going to be great. And there's really a lot of potential gain there. NUMA has also driven what Jeremy Cole called this NUMA swap insanity, where basically, because now you have your memory split in two, if one of the nodes fills up, then you start swapping, like if all your memory had filled up. So, you have to be careful and balance your allocations so you won't run into swap issues due to NUMA. You can check this if it's balanced using, NUMA control hardware, and you can fetch stats through NUMA stats and VM. All right, we're gonna skim through this very, very quickly. Basically, I introduce and mention some tools that are the most advanced and most up-to-date tools to look into memory performance, including eBPF. This is super advanced. It's not what you're going to be using directly, but it's the basis for many of the other tools. BCC is the BPF Compiler Collection. This is a front-end, a collection of scripts based on eBPF. And it has many ready-to-use scripts. We're going to be looking at some of them. I strongly recommend visiting their GitHub repo and checking their examples in the tools. It's great. BPF trace. This is the dtrace of the Linux world. We're going to be taking a look at a very quick example today as well. This is amazing. This is what we should all be learning. This is the easy way to use BPF. Really allow us to look into the full stack with a single line of code. Really, really great. And perf, this has been around for a long time. It allows us to do sample-based statistics collection and counting as well. It really allows us to see a lot of the events in the kernel and the performance monitoring units in the CPUs. It's one of the tools we're going to be using today as well. Again, this is something you should be learning if you're interested in performance. And with that, let's go on to utilization. So utilization, it's divided into concepts, basically. Throughput-based, so how much of my bandwidth I have used it. Like every system component, such as a disk, can deliver a certain amount of throughput. So when, let's say, my disk can deliver 100 IOPS, so if I'm using 80 IOPS, I'm at 80% utilization based on throughput. And also my disk can be a 1 terabyte disk. So if I use it, half a terabyte, I'm 50% size-based utilization. So in this case, we're going to be looking at memory. Throughput has been, I guess, a mystery for memory for a long time. Like everybody will ask you, how do you look at throughput with memory? We're going to be looking at that. And then size is how much of your memory is used. There are a few, this is a simple percentage, but there are a few things. You can have your resident set size, your working set size, and then one that I'm not mentioning here, which is the virtual set size. If this utilization, if the size-based utilization, well, if either utilization goes too high, nasty stuff will happen. We're gonna see scanning and paging, which is gonna slow down all our operations, where we might suffer out of memory killer. And I didn't forget swapping. In Linux, there's not such thing as swapping. We only have paging because we don't swap out. We don't page out a full process, just a part of it. Swapping is like taking out a full process out of memory. So I didn't forget swapping. I just mentioned paging. But again, so we don't want utilization in either way to go to high. If throughput-based utilization goes to high, then you will suffer stalls, which is the last part of our talk. Okay, this is the resident size. Set size is the simply estimated with this formula. It cannot exceed the total size, and there's tons of tools. You can use free-m, vmstat-1, ps, AXO, and then show the command, the RSS, and the percentage of memory. And then you could look at it at the top. Super easy. This is the one you're most familiar with, more likely. Then the working set size is how much is really in use. Like I have my database, which is 1 terabyte, and I only have 128 gigabytes of memory. But you know, I only use the data from the last week, which is perhaps 50 gigabytes of database. So that is actually my working set size. In this case, you know, it's as long as it's less than the total memory, it's all good. If it's you know, near the total, you're gonna start seeing sustained scanning, and if it's greater than the total, you're gonna see paging and swapping. It's not always easy to measure directly, but we can infer from these effects, and usually, you know, we can tell, okay, you're using more memory than you have. But there are some tools, all of them written by Brendan Gregg. WSS, PL, they're all in this website. Again, you can take a look. It's not something you will be usually looking at very often. Rather, again, you take a look at the effects, especially scanning. It's something you will be looking for. When scanning is when the VM cannot find free space, and it's the first sign of saturation. There's a SAR-B, SAR-H, SAR-B, I guess, that will let you observe the scanning. We're gonna see paging out, and if there's like extreme pressure, we're gonna see paging in, where something that was previously paged out was accessed. And this is the worst sign of saturation before you get OOM Killer to kick in. But basically, paging in is what people call swapping. Scanning, this is done by a process called kswapd. And if your memory utilization ever reaches mean 3 bytes, it's going to do it in sync mode, and your OS is going to be frozen. There's an LRU list, and it will try to evict inactive pages from there first. Should not normally happen. So if you see it, suspect something is bad. Again, yeah, SAR-B. And then perf tools from the BPF perf tools book has VM scan for BPF trace. Again, very easy to use. All right, paging. This is what you see in VMstat under the SISO. You can adjust the behavior with VM swappiness. And yeah, SAR-W is another way to look at paging. And let's go for more interesting stuff. These are the conditions under which OOM happens. Usually, OOM happens because we really have a lot of memory pressure, which is the only reason you will hit all of these. I'm not going to read them. You can go through the slide very quickly. But yeah, the OOM killer is the last resource to free memory. It will terminate your process because it grew too much, and the VM had failures to allocate memory in the last 5 seconds, you know, multiple failures in the last few seconds. So this is really bad to see. You can use the BCC tools OOM kill to monitor the events. You can also see them in vmessage-t or journal-ctl-k, and usually in the var log messages, syslog, or kernel logs. Okay, to a more interesting part of our talk, stalls. So what is a stall? As I was saying, RAM is the new disk. It has become so slow when compared to the CPU that we are in fact memory bound most of the CPU time when talking about databases, right? Other computer things, you know, other computer disciplines probably don't suffer as much. But gladly, CPU pipelining avoids a massive waste. And it usually is what limits memory stalls, is what usually drives, what usually limits the throughput scaling. Diagnostic info is usually easy to obtain with perf, but sometimes it's hard to read or to fully interpret. So we're going to take a look at this in a second. But let me speak about CPU pipelining before. So I was telling you that there are stalls, and the stalls happen in what is called the CPU front end and the CPU back end. The CPU front end is where these two stages are carried on. The fetch, where you fetch the instruction from memory. So you load your program, your binary to memory, which is full of instructions, and then you have to fetch those, put them into memory for the CPU to decode and execute them. So this is the front end, this is the back end. So when we have stalls, is because one of these cannot fetch memory fast enough. And the pipeline helps with the poor memory performance because it allows us to execute multiple instructions in a single clock cycle. So if you look, the clock cycles are in the verticals. And here are the instructions that will be executed. So in the first clock cycle, I got the green instruction on the fetch. And on the second clock cycle, I got the green instruction in the decode phase of the pipeline and the purple instructions in the fetch. And they are both executing in the same clock cycle. So this allows the CPU to save a lot of time and to make better use of the resource of the CPU. This is what's been saving us along with the level 1, level 2, level 3 cache. And it's very important. And it's actually where the stalls happen. And these are our basic tools to look at stalls. So I'm gonna very quickly, just one second. I'm gonna show you, oops, sorry for that. Gonna take you to a terminal, woohoo! And I have a sandbox here. We're gonna also be running a standard performance measurement tool with benchmark, which is called Stream. It's written by John Sculping from Texas University, if I recall correctly. And basically, what screen dash is demo. Yeah, sorry for this. Promise it's going to be very fast. Oops, this is very bad. Okay. And it's not so bad. I can fix it. Okay. Go to the jam post. And then from there, let me go to my demo. Okay, now I have both. Let me bring, there you go. So I was telling you, I'm going to be running stream. I compiled stream today to run 1,000 million elements 10 times. And stream is going to tell us how much bandwidth my system can do. And at the same time, I'm going to perform memory bandwidth, perf stat dash d dash a dash memory latency and memory bandwidth every 1,000 milliseconds, and I want the metrics only. So this, what you don't like? Metrics only. Metrics only. There you go. Oh my God. Just let me check my own command. Metric only. I'm sure I'm doing it right. And I did it on this same machine. Oh, there you go. I knew I was right. There you go. So this is giving us the real latency here. This is expressed in CPU cycles. And it's telling us every time I miss a hit on the level 1, level 2, level 3 cache, how many cycles do I spend going for a load? And then it's telling us the bandwidth for level 1, level 2, level 3 cache. And if I and the access bandwidth for the level 3 cache. So there you go. Why are you behaving like that? Behave. Come on. And then I'll leave that one there, and I'm gonna run my stream, and the stream is gonna local stream. I was fairly sure it was there. So it's going to start running, and it's going to give us, okay, there you go. It's telling us, okay, best rate I could get when copying data from one array to another, which is basically what a stream does, was 125 gigabytes per second. And then here, we're going to see actually that was, fairly close to what we're seeing, 139, give or take. It's, well, look, 139 for the triad, which is a series of operations stream does on the arrays. The values are very close. So this bandwidth measurement does match what operations we are doing, because this bandwidth measurement is done like that. Like I copy 1 megabyte of data, I take how much time it takes to copy that amount of data, and then I can infer the actual bandwidth available. So measurements are good. So based on that, here we are. This continues to escape me. Okay. So what we're gonna do is I'm gonna run a sysbench. Oops. Oh. Give me a second. I'm trying to copy that. There you go. Okay, I think everything is ready. Oops. Wait, just give me 1 split second. There you go. And with that running, we should see here, I'm actually going to start it again. And we're going to see a bit of how this MySQL, it's warming up. It's hitting disk like crazy. You can see it's doing barely 0.2 queries per second. So it's starting to warm up the buffer pool. It's reading from disk. So, it's not being able to throw a lot to the memory. That's why we see such low numbers here yet. I'm also gonna start looking at the actual IPC, the instructions per cycle. -A -D -I1000 -B, and I'm gonna be taking a look only the -X MySQL at the MySQL process now, not at the whole system. There you go. Oh, sorry. Dash metric only. Beautiful. So, whoops, there you go. That looks more reasonable. Okay, so this guy is doing more than one instruction per cycle, which is what we spoke about before, about pipelining, right? Is suffering very low level 1 cache misses. It's suffering some last level load cache misses. We could also take a look at branch miss predictions and the TLB. But basically, the one metric you always want to look at is the IPC, the instructions per cycle. This metric is basically the indicator of your CPU being stale on memory or not. So when it's below 1, basically it was unable to complete one full instruction in a cycle because it was unable to obtain the data from memory that it was required to complete that instruction. So when we see more than one, it means that it was able to complete the instruction and fetch more data to actually perform some other part of another instruction. So a higher number, up to 4, which is how many instructions in a single cycle a modern CPU can do, is what we expect to see. Now, if we see 4, it's likely because it's spin looping. So you usually will expect to see something like this: 1, 1.4, 1.5, 3.70. Usually means it's totally stale on disk or it's doing very little work. You can get a much more detailed. Let's remove metric only, and let's remove the interval, and let's add more detail. And let's count to 5. 1, 2, 3, 4, 5, and hit Control-C. And here we have like a summary of those few seconds, 6 seconds during which I captured data. It did this amount of instructions per cycle. It tells you about the branch misses, level 1 and level 3 cache loads and misses. The translation look-aside buffers and misses. The instruction, this is for data TLB and for instructions TLB. The same goes for the level 1 cache, data cache, instruction cache. And again, here is how many instructions, how many CPUs were utilized as we ramp up the test, and this goes to a better place. We should start seeing that more CPUs become fully utilized. So when does a stall happen? Well, you basically will see this below below 0, and then let me see if I add another D here. 1, 2, 3, 4, 5. Why are you not showing me? Okay, usually perf will show you that. With perf, you can do perf list, and you can see all the events you can trace. So, for example, if I want to trace stalls, I can look for stall events and cycle activity stalls total. I could do something like this, and do perf stat dash d dash. So this will basically give us the number of cycles that were stale for some reason. In this case, I think I got the wrong counter, and I think 80% is certainly not what I would expect. Albeit there's a ton of LLC misses, but I wouldn't expect to see that many stalls anyway. Let me check one very quickly. All right. Content portion. Well, this is particular because usually front end usually I will see front end stalls, back end stalls as part of the regular perf output, but it's not being the case in this. I should take a look and see which of every time you set up perf, it's and in a kernel and in a particular CPU, you get different capabilities depending on the kernel and the CPU. And in this case, apparently, it's not in this kernel's perf to have the front-end stalls by default. It usually will show you by default. Anyway, as this has ramped up more or less, I want to, oops, sorry for that. I want to look at memory bandwidth again. Here, memory bandwidth. You're gonna see that it's already you can see now it's doing quite a bit more bandwidth. So it's starting to actually become memory bound. So it's not longer only IO bound as it was before. It's starting to become memory bound. And we are gonna see that there's more there are more a lower IPC as this. So the IPC is gonna tend to go down as we become more memory bound. So I'm gonna let this run for some minutes while we go back to our slides and we talk about leaks. And we're gonna go back to this demo on stalls, but I need to let that thing warm up for a minute, and I only have 17 minutes left, so I want to take the time and go through the leaks slides. Perfect. So leaks, what is a memory leak? Basically, memory allocation is done by the memory allocators, and you will allocate and then free memory. That's the basic operation. So a leak is when we allocate and then never free the memory. So sometimes people confuses excessive growth with leak. So for me, one of the most important things to do is to start by characterizing the growth. So a simple loop with PS, showing us the RSS and the percentage of memory the process is using, every 5 seconds, and let it collect data for some hours. This is like the first thing I do when someone tells me I have a memory leak, because I need to understand if the memory ever is given back to the OS, or if it's really growing in a permanently monotonically increasing fashion that never gives up the memory it has taken. We also have to look at the configuration. It's like, did you allocated 120 gigabytes buffer pool in your 128 megabytes machine? Then, it's likely you're gonna end up using all your memory. And it's not because there's a leak, it's because there's a misconfiguration. Excessive growth is something used an unexpected amount of memory, but it gave it back. Misconfiguration is I screwed up my configuration, so I used way too much memory. And a leak is something is giving memory and never returning to the OS. We have a few tools, and I missed one that I want to show you today. But basically, this is the one I use this I use very often. Perf record, and what I do is I record page faults. So I only record this event, and I only record for the PID of my interest. So with that, I can quickly and with relatively low impact, because I only sample at a frequency of 99 samples out of 1,000. So here's what I will do. I will capture some data, perf record during a normal workload. And with that, I will produce a flame graph, and I will type it no leak. And then again, when the problem is happening, or if I know which query is the one that causes the problem, I will go and record again, and this time I will call it leaking, and then I will produce flame graphs. Here is the flame graph when the memory is not locking. You can see it's doing some temporary tables, HA heap, that's the memory engine in MySQL. It's doing some sub selects, whatever, but mainly it's doing temporary tables 99% of the time. So this is normal behavior, and this is bad behavior. So this is the green is the delta. So I colored that based on the function names that did not appear on this one. So I took a sample, and all the functions named that appeared during this workload, they will still be colored orange, red, yellow. And the ones that didn't appear during the normal workload time are now colored green, bluish. So I can tell that there's something in the storage of blobs and copying well-formed charts that is actually causing a memory leak. And we're gonna see this in a second. Oops. So let me see where this is. So you're there. I'll let you leave. This guy, look at this guy, how it's probably now, oh, still 120. Okay. I should have started warming up that way before. Doesn't matter. I have CD sandboxes, NSB 5636. Demo leak. Give me 1 second, please. Okay. Demo steps. All right. So basically, I have a demo monitor RSS. Oops. R sandbox. Oh, did I put it in R sandbox? Why? Why did I do that? Why would anybody do that? How much time do I have, Philippe? 10 minutes. Sandbox. Babies.
Yep, 10 minutes.
Thank you, Philippe. I'm good on timing anyway. I have this configured properly? No, this is not configured properly. Okay. Just 1 second, please. Then master. Oh, I know. I have this one configured properly then? No. There you go. Just one very quick reconfiguration. Okay. One thing. So restart. And now, come on. Demo RSS stuff. Demo RSS. Jesus. Kurwa. Sorry, but I obviously did something wrong. Jesus, kurwa. My mom always told me don't do live demos. 2237. Why are you so mean with me? This was... All right, Jesus. Okay, so it's running again. I, have that monitor, and it shows that it's not consuming memory in excess. I'm just gonna start one more terminal, and I'm gonna connect there. I miss it, right? Yeah, why not? There we go. There we go. Okay. Okay. So basically what this does is it creates a very simple database, and it then inserts some very large rows. And you can see it immediately started growing the RSS. And these aren't running yet. And if we, and there you go, you can see it continues leaking memory. And so what I'm gonna do is I'm gonna stop this monitor now that you saw that it's continuously leaking memory. And I'm gonna go with perf, with user share VCC tools memblik -p cat root sandboxes sandbox master. Oops. And then I'm going to do -o, which is only allocations older than 15,000 seconds, and only the top 5, please. So this guy has attached to the MySQL PID, which is losing memory. You can see it's the same PID, right? And it's gonna take a look and say, okay, which threads allocated memory, which code paths in these threads allocated memory and then never gave it back. And here it already found some. And basically, we can see it's doing a dtuple convert big record. And I know through code analysis that this is related to handling of blobs, which is, again, the same thing I saw on the FlameGraphs. So again, this simple tool does that. It looks at which backtraces, it said, okay, this backtrace, this specific sequence of functions led to a memory allocation that was later never freed. A free was never called for the memory allocated here. And so with those two, you can very, very easily see how memory is leaking. And you could also, again, do the BPF trace, BPF trace, come on, -E. Where is it? I don't have it. Come on. But basically, you will do this. Let me copy paste from here because I already have it. Basically, so you do the BPF trace -E, and then the event you want, or the probe, rather, this is called the probe. Then which filter, on which filter you want. I should get the PID for, you know, the process we want, which is this, whatever. I'll get it in a second. And then what I want to do when this probe, when we hit this probe for this filter, what operations I want to do. In this case, I want to get counts of the user land stack traces. And I want the output to go to this file. And this will give us a lot of traces. I'm not gonna run it now because I already have it here. I have these stacks. BPF trace. I know I have like 2 seconds, Philippe. So I'm hurrying up. These stacks were unresolved, so I had to do some trickery to resolve it. Now they are fully resolved, and they have the function names. And based on this, I was able to create FlameGraphs, just like I did from perf. Okay, so time is up, and I won't be able to show you everything I wanted. Damn it. Just one last D-A-B cat sandboxes SD5 17 that 1, 2, 3, 4. And this is still, yeah, still warming up the buffer pool. Damn it. Usually, when the buffer pool is fully fully warmed up, in this here, the memory bandwidth will not reach 200 yet. Yeah, it's still 150. So I know this machine can deliver like 300 gigabits per second of memory bandwidth. When it reaches around that, we will see the IPCs go below 1. They go into like the 0.6 range. All right, my time is up. Was a pleasure having you here. Thanks so much for attending. And if you have any questions, I'll hang around the Percona Live Slack for a few minutes. Have a good one, everybody. Bye-bye.